the view or the other one? You want
You do 17?
And 16.
17 and 16? And do you know what those are?
Find the limit of 4x minus 3 is x equals 3, then find delta greater than 0 such that f of x minus
Is this what we're doing? Is it
Yeah.
an epsilon delta one?
Yeah.
Okay, so limit as x goes to 3 of 4x minus 3? Is that right? Did I tell you the limit or do you have to figure it out?
So then find delta greater than 0 such that the absolute value of f of x minus L is less than 0.1.
Oh, so epsilon is going to be, so that's going to be 11. And our epsilon is 0.1. Okay.
Well, what?
Is it 4x minus 3 is our function?
Yeah.
And so that its limit as x approaches 3,
Yeah, 12 minus.
12 minus 3, as you see if you paid attention. Well done. 9, okay. All right. So you're always going to start with this and try to end here. So to start here, we're going to plug in the f of x, plug in the L, plug in the epsilon. So the f of x is this, so that's going to be the 4x minus 3. Oops. And the L is the 9, and the epsilon is 0.1. And then it helps to, I think, know where you're aiming, you know, what's your goal. So our goal is to get to x minus, and this number is the c that we're approaching. So that's going to be the 3. And then whatever we get is going to be, well, that's not epsilon, that's going to be the delta. So whatever we get is going to be our delta. And in this case, it's going to be a number. Since we're starting with an epsilon that's a number, we'll end up with a delta that's a number. On the next one that I think Tim's asking on, the epsilon isn't given to us, so it's just going to be the symbol epsilon, and our delta then will be in terms of epsilon, epsilon over 2, epsilon over 3, something like that. Okay, so far? Brandon, we all right so far? Okay, wait a moment. Okay, so we'll just combine those. -3 minus 9 is going to be 12. So then what?
Take the 4 out.
Yep, factor the 4 out. So, and you can do it, I mean, you can do it in one step if you want. And the product inside an absolute value is the absolute value of each one separately. The absolute value of 4 is just 4, so it comes outside. And so now we're making progress because now we're headed towards what we want in that absolute value, which is the x minus 3. So we'll divide the 4 to the other side. And so don't leave it like this. I mean, on an AP exam, well, you wouldn't do an epsilon delta on AP, but they don't care if you simplify, but your math teacher does. So you can either make it into a fraction, like multiply top and bottom by 10, to move that decimal over, or you can just divide it out. And so do you know what that is going to be?
0.024.
Yeah, so since 1/4 would be 0.25, 0.1 divided by 4 is 0.025 here. Okay? And then we're done because now this is our delta. We have found the delta. So if we want all the values of our function to fall within 0.1 of 9, we'll choose all the x values to be within 0.025 of 3. That's what that says. Okay, tackle the next one. Is that the one you want to?
Yeah.
Is that another epsilon delta then?
Yeah.
Okay.
I'm not exactly sure what the problem is. The
Brad,
limit
do you
of
have it?
It says find the limit L. Use the epsilon delta definition of the limit to find and prove the limit of x squared. I don't know if it's plus or minus because mine's printed weird. But L.
Okay, I think I got mine up here somewhere.
I think it's as x approaches -3.
-3? And is it just x squared or x squared plus something or minus?
I don't know, there's a gap on mine.
It's just x squared.
It's just x squared
But it's equal to L.
equal to L.
Yeah. Okay. Okay, and again, we're gonna, start with the, so you don't have to memorize this, I'll give that to you for all values of x that are less than delta. Okay, so when I didn't give you the L, but that's not hopefully hard, you just direct substitute in the -3. -3 squared is 9, so our L is gonna be 9. So we're gonna start with the absolute value of f of x, which is x squared, minus the L, which is 9, less than epsilon. Our goal is to get to an x minus -3, which will be an x plus 3 less than delta. Okay, so far? So this is the one where there's a little bit of a trick to it. So about all we can do with x squared minus 9 is to factor it. So we'll do that. And so that's x minus 3, x plus 3 less than epsilon. We're trying to get to x plus 3. So we got to do something with this x minus 3. We can separate this out if you like. You don't have to write this stuff out, but it might make it more clear. I don't know. Now, we can't just divide the absolute value of x minus 3 to the other side, because for the wrong choice of x, that would be dividing by 0, which isn't defined. So here's where we have to be clever and say, well, let's see, if we're trying to approach -3, all we really care about is the values of x that are really close to -3. That's what we mean by a limit. So you can choose what you mean by close to -3. And for us in here, usually close, we go 1 on either side, that's close enough. Because our function is not going to do something really crazy in between, a distance of 1 away from where we're taking the limit. If you had like a vertical asymptote or something, you might have to be a little more careful. You might have to narrow it down more than just within 1. But for the ones that we are going to do, we're just trying to get the idea. So you have to communicate. So we're going to say, okay, for if our -3 is here, then 1 on either side of -3 means from -4 to -2. So for the values of x that are in between -4 and -2, then what is the largest that this absolute value of x minus 3 could be?
Wait, what?
So we're 1 away from -3 for x. So for those choices of x in between -4 and -2, what's the largest the absolute value of x minus 3 could be?
7.
7. It's going to have to be at one of the endpoints. Okay, so at -2, we would get -5 in here, absolute value would be +5. But at -4, because of the -3, we'd get -7. Absolute value is going to be 7. So, since this is the only this is our whole world, we're only concerned about the values of x between -4 and -2. Then now we can come back up here and we can create a chain of inequalities. So we're trying to get to this to be less than epsilon. So this x minus 3 times x plus 3 in absolute value. Now, if we're saying that x minus 3 is less than 7, then the absolute value of x minus 3 times x plus 3 must be less than 7 times the absolute value of x plus 3. True? Is that reasonable?
Yeah.
Yeah. I mean, if it isn't, I can try to explain more.
Can you explain it more?
So if we have two things, so if we had, so we've had a number x and you multiply it by 6, that has to be less than if I multiply that x by something bigger than 6.
So is that why we look for like the max absolute value instead
Yes.
of the minimum? Okay.
Yes, we want the largest this can be, because we're trying to create a workaround this whole absolute value of x minus 3 thing that's a problem because of the variable. That's the whole issue. And so, because for different values of x, it could be just about anything. So if we say, well, we don't really care about what happens away from -3 because it's a limit. So let's take away all that noise and just say, let's just narrow in on around -3. So then we can say, okay, now we can say on this interval, then this can't be any bigger than 7. So therefore, this times this must be less than 7 times this. Brenda, is that okay? Well, that's great, because what we're trying to do anyway was to divide that out of there. Well, we couldn't when it was a variable, but now we can. So now we can just say, well, we can divide by 7. And so now we've got it. So now what this is saying, I mean, this is really a formal mathematical proof that the limit as x goes to -3 of x squared really is 9. Because what our definition, our epsilon delta definition is saying is, for any value of epsilon, so for any value of epsilon, we can find a delta so that we choose values of x to be within this delta of -3. Narrow that down. All those values of x are going to be within that epsilon of 9. And it's flexible because you can change your mind about what epsilon is, and we can still adjust our delta so that it will still work. So if you choose epsilon to be 0.1, we can say, okay, choose the delta to be 0.1 divided by 7. Get that close to x equals -3, all of y values will be within 0.1 of 9. You change your mind, you want the epsilon to be 0.0001, no problem. Here's what you're going to use for delta. We're still going to meet that criteria. All the values of x will be that close to 9. We'll give you values of y that close to 9. And that's the proof. So we have shown for every epsilon greater than 0, there is a delta where this will work. And it only works because this is getting closer and closer to 9 as the x value gets closer and closer to -3. We couldn't have done that if it didn't really work. And if it didn't really work, we couldn't have done this. So it is a definition. It works both ways. Okay. That help a little bit? We can do more too after school. Other questions on the review? Other questions on the whatever the next homework was?
16?
Yeah, 16, yeah, homework 16. That work okay? Brenda, we okay on those? Okay, so we're going to go on then, and we're going to talk about 2.2 derivative of. So reinforcing a little bit what we talked about last time and clarifying this difference between an average rate of change and an instantaneous rate of change. So it's a big deal. So the average rate of change is something we talked about over and over and over again in AP Prep, in pre-calculus. Instantaneous rate of change, that's what we're going to talk about over and over again in this class, in calculus, because that is a calculus topic, one of the big ideas. So the average rate of change, we said again, the average rate of change of f, a function f, from x equals a to x equals b is given by that, or I'm sorry, let me say, from a to x equals a plus h is f of a plus h minus f of a all over h. So we're trying to really emphasize and get comfortable and clear on this kind of notation things. We're changing, last year in AP Prep, we really tried to move from y2 minus y1 over x2 minus x1, which is exactly what this is. It's just a slope formula, which is an average rate of change, to more functional notation, f of b minus f of a over b minus a. And we did in AP Prep, and especially now, to this notation of f of a plus h minus f of a over h. when we use the a's, we're talking about this being a particular number. And when we use an x there, then we're talking about making it more of a function. Okay, so we'll kind of bounce back and forth between the two of those. So the instantaneous rate of change, I'm going to change the color for this. So this was average rate of change here. So notice on the average rate of change, there is no limit. It may seem like a little thing, but it's huge conceptually. So the instantaneous rate of change and these are the problems. This is one of the big problems that Newton and Leibniz were wrestling with that previous brilliant mathematicians couldn't resolve, but Newton and Leibniz figured out in the 1600s, the instantaneous rate of change, which is the same thing as what we are going to call the derivative. One of the two big ideas in calculus. So we say that the derivative of f at x equals a, and here is the beginnings of many different symbolic representations of this notation. We will write as f prime of a. So we'll read that as f prime of a, or the derivative of f evaluated at a is going to be this limit. So now it's going to be just like what we just wrote up there with this average rate of change, or sometimes called the difference quotient, except with the huge difference that has got this limit in it. So it's f of a plus h minus f of a all over h. So it seems like a little thing, but it's really, really a big idea. And so when so it's a limit, right? So this limit may exist or it may not. And that's part of what we're going to tease out in the next few days and weeks is, when does this limit exist and the derivative exists? When does this limit not exist and the derivative of a function not exist at that particular value of a? So when this limit exists, trying to expand your vocabulary here. When the limit exists, we say f is differentiable. F is differentiable at x equals a. So a function may have a derivative at some points and not at others. And so it's an idea of differentiability. So there's a kind of a picture that goes with this, and I want you to have a mental picture, an idea of what's going on kind of behind the scenes here. So here's our xy axis. Here is our generic function, y equals f of x in green. And we are talking about, here is our x equals a right there. And so what we are interested in, what the whole idea from Newton and Leibniz is, they wanted to know what is that slope of the tangent line to the curve at that point. So that m, it turns out, is exactly what we're going to call f prime of a. So we're going to learn a few of these applications. So the derivative evaluated today is the instantaneous rate of change of the function at x equals a. It's also the slope of the tangent line to the graph of f of x at x equals a. And so what we were seeing before, what this means visually is here you've got a point A, and then you're going to go some finite distance h away from A. H could be positive or h could be negative, either way. So this point we're going to call x plus h. And I've just shown it to be where h is positive, but doesn't have to be. And you run up to the curve, and so this point right there is where we have that point x coordinate x plus h and y coordinate f of x plus h. And so what we were seeing in the case of the average rate of change, we're talking about the average rate of change of that function between x equals a and x equals x equals a plus h. Sorry about that, I didn't write that right. Let me back up there. Call that a plus h. Sorry, fix that. Okay, we'll try it again. So the average rate of change of this function from x equals a to x equals a plus h is that slope of that secant line. So when you look at the line that goes from two distinct points on that curve, that's an old pre-calculus idea. That's it, we'll call an average rate of change. It's the slope of the secant line. So you have kind of two different interpretations of that. Once we push that h to 0, we move that point over and over and over, and then if we can take that limit, if that limit exists, then what we find from that limit is either we can call it the instantaneous rate of change, or we can call it the slope of the tangent line, or we can call it the derivative f prime of a. So we're going to do this kind of stuff, with these limits and find that. Sometimes with this being a number, and we're going to find the actual derivative at a particular point. Sometimes we're going to do that with this being an x, in which case what we're going to get is an f prime of x, a new function from the old function. And so there's kind of two different ways of going about that. Okay, so let's look at a couple of examples. So we're going to find a derivative, and then from there, what we will do a lot is we're going to find the equation of that tangent line to the curve. Okay?
Can I run to the bathroom real quick?
Yes, go ahead. So we are going to find the derivative of f of x equals sine x at x equals pi, and we're going to do this one numerically. So this is like what you were doing in your last homework. And then after we find the derivative, we're going to use that derivative and find the equation of the tangent line to sine x at x equals pi. We're going to find the derivative, let me say, numerically. And we're going to come back and do it numerically. Then we'll come back and do it analytically, which is where we're going to live a lot more of the time in here. All right, so thinking about what you might have done on the homework last night, if we want to find f prime of a, which is pi, and we're going to approximate this using our calculator and some kind of idea of this f of a plus h minus f of a over h. What might we choose for h?
Pi over 2?
No, so what we're going to do, we're going to be doing this. So this is our approximation to f prime of a. So what we did, if you saw the video from yesterday, that when we started over there with a table of values, and we were one away, we were trying to find the rate of change, instantaneous rate of change at the height at time 1. And so we first used the table, we were one away. And so we looked at what is the height at 2 minus the height at 1, or the height at 1 minus the height at 0, or height at 2 minus height of 0 over 2. Then we said we can do better if we took an equation. We got the height equation. And then we said we could do h of 1.01 or h of 1.001 minus h of 1 all over h. So if we take a very small value of h, then we can get pretty good accuracy here. So we can choose an h of 1, but that's not very small. So we're going to be much better off if we take this to be very small, and as we'll see in the days that come here, our calculator actually gives us a numerical derivative. It does this to try to get an approximation, and it will usually use h in the neighborhood of 1/1000. So if you choose h to be something like 0.001 or smaller, we will probably get enough accuracy to do just about anything we want to do in here. Okay? So let's do it with, let's just choose, I'm not sure where exactly this will take us, but let's try h equals 0.001. And if it doesn't work with enough accuracy, I may come back here and we'll go smaller than h equals that. So then what we're going to do, what's this going to look like? What's our f of a plus h minus f of a all over h going to look like? If that's our function, we want to find the derivative here, and this is our average rate of change. So tell me what to write down.
Yeah.
Sine of
Sine of pi plus 0.001.
exactly. See where that's, the a is going to be the pi where we're trying to get the derivative, or approximating the derivative. We've chosen h to be 0.001 minus, what's the f of a going to look like?
0.
Yeah, sine of pi, you're right, which is 0. I'm just going to write it out though, and then all over 0.001. Okay, so do that on your calculator, and when I did this before, I used an even small one. Like I think I have like 5 zeros, 0.00001, and then I got exactly what we needed. Let's see how accurate this is. And we know sine of pi is 0, so you can, on your calculator, evaluate the sine of pi plus 0.001. We know that's minus 0, and divide that result by 0.001. Make sure you're in radian mode. Make sure you're in radian mode. We're always in radians here. You get a very different answer for degrees. Anybody have it? So negative 0. How many nines you got? 6 nines?
8, 3, 3, 3.
Good. This is what I was hoping for. 1, 2, 3, 4, 5, 6. Anyway, so we're going to round to 3 decimal places. So if we round to 3 decimal places, what will this be? Negative 1. Yep. So we're going to say, for our purposes, that is equal to negative 1. And that, we know, is the slope of a tangent line. That's also what we're using. We're going to say f prime of pi is approximately. We don't know if that's exactly right yet because we approximated it. Turns out that is exactly right, but we'll find that out later. Is that okay so far? Okay, so now we've answered part A. We have found the derivative of this function at pi numerically. This is what we're doing. Now, how do we find an equation of a tangent line? Well, this goes way back. How do you find an equation of a line? What pieces of information do you need? Slope, well, which we have. So we got the slope. And what else do you need? To find an equation of a line.
The b?
The b, or what else would work in the event that we can't get b?
A point.
Any point will work. So let's find a point. What's a point that, and it's not just any point, because we're trying to find the tangent line at the point of tangency. So it's got to be at pi.
So pi sine pi.
Yeah, exactly. And we happen to know sine of pi is
0.
okay. So now we have point and slope. So we can say y minus y1, which is 0, is going to be negative 1 times x minus
x1, which is pi, and you're welcome to leave it like that, or since we're so close, I guess we go ahead and write it in slope-intercept form. Okay? This is something we're going to come to over and over and over again, find an equation of a tangent line. Okay? In fact, we're now going to do one, instead of finding the slope numerically, by approximating it on a calculator, we're going to do it analytically. Okay, so we're going to find the derivative. So let's find the derivative. And maybe I should show, let's just real quick take a look at what a graph, so we see, I'm not sure if we see exactly what's happening here. So here's our sine curve, right? And it's going to do that loop above, loop below thing. And there's our pi, and that's 1, and that's -1. So there's our sine curve. So what we've just said is that at the point pi 0, at this point right here, the tangent line, and it's kind of hard to think of, it takes a while to get used to what we mean by a tangent line in calculus versus a tangent line in geometry. Because in geometry, a tangent line is always with respect to a circle. So in geometry, you say a line that intersects a circle in one point is tangent. Well, it's not quite the same in a function, because if we had a function that did something like this, and we found a tangent line to the curve here, it's going to intersect the curve here, but because the line is infinite, it may end up intersecting the function a second or third or many times. That's okay. It doesn't. This is still a tangent line because in that little neighborhood around there, it is just grazing the curve, if you will. So here, our tangent line, we're saying, has a slope of -1. It's looking like this, which seems really weird that that's a tangent line in the context of what we know in geometry. But for our purposes, that's what's happening there. That is our tangent line to the curve. A line at pi 0 with slope -1. Okay, you can also see that as this curve, as you're moving along this curve, we're seeing the slope is also the rate of change. So the rate of change in here, this function was growing, it was getting bigger. The slopes of the tangent lines are positive. It's an increasing function. Right at the top, for a moment there, it just is paused. It's not increasing, it's not decreasing. Its rate of change is 0. And then it starts to decrease, and the rates of change are negative. And that's what we're seeing from there. Okay, so let's do some other examples here where we're going to do this analytically. So we are going to find the derivative, we'll say analytically. And then we are going to find an equation of the tangent line to the curve at the given point. So what I'm going to do is I'm going to give you, we're going to do this a few times, I'm going to give you different kinds of functions, because it looks a little different when you're finding the derivative analytically, depending on what the function looks like. And I'll give you a point for that function as well. Okay, so the first one, we're going to say we've got f of x is going to be 1 over x plus 1, and we're going to find the derivative and the equation of the tangent line at x equals 0. That's our value of a. All right. Any idea how we're going to start this thing?
You said f prime of x?
Okay, so f prime, more particularly f prime of
A.
And what is our a?
0.
Okay, so we want exactly f prime of 0. Okay, so our definition of the derivative at 0 is going to be, what does that look like?
F of a plus b.
Okay, and we're missing something important before that, because this is not the average rate of change, it's the instantaneous rate of change. So what little detail that's really critically important do we need? the limit, we're gonna take the limit as h goes to 0. Okay, so we need that. Okay, and then keep going around, it's gonna be f of,
A plus H,
okay, and what's the a?
0,
0 plus h, exactly, minus
F of H,
f
Oh,
of
F of
0, good, all over h. All right, you with me? Okay, so should we do it together, or you want to get a shot at it first? Oh, I think my mic cut off there for a moment. Let me repeat that. Should we do it together, or you want to give it a shot? I'll give you a head start. We'll go ahead and start on it. I'll give you a lead time of a few seconds here, and then I'll jump in. But I'm not going to say anything at first, so you can still think. Getting a common denominator in here. So at some point you're going to have to get a common denominator between 1 over h plus 1 and 1. So you have to multiply top and bottom by the h plus 1. How we doing? I lose you? Should we back up? So here, so back in the beginning, here's our f of 0 plus h. I'm going to plug in 0 plus h in place of that x. So there's 1 over 0 plus h plus 1 minus 1 over 0 plus 1. It's just going to be 1 over h plus 1, and that's really just 1. Still over h, still taking the limit. So here we have to get a common denominator between these two fractions. So the 1, we're going to multiply top and bottom by h plus 1. And you can just leave that one the way it is. So we get our common denominator of h plus 1. We have this one minus, and then we're going to multiply through by that h plus 1. Still all over h, still limit. Okay, so then I'm going to say we got the limit as h goes to 0. So distributing that 1, we're going to get a minus h minus 1. The 1's will cancel. So minus h. So now this becomes just a negative h over h plus 1. And that's still all over that h. I'm going to divide by h is to multiply by the reciprocal. So this is going to be a negative h over h plus 1 times 1 over h. So when we did this in AP Prep, we always knew that we were finished when we got the h's to cancel. But now that we're in calculus, we're not quite done yet because we still have to take this limit as h goes to 0. And as h goes to 0, we direct substitute in h, we just get negative 1. So I guess we've learned all derivatives are negative 1. I'm just kidding. So we've got f prime of 0 is negative 1. Okay? That's our slope of our tangent line. The point, we're going to use that same value of x0, plug that into the function. I should use something other than x plus 1, and we get 1. That's our y-intercept because it happens to be 0, 1. So our tangent line is negative x plus 1. We better do something other than negative 1s and 1s here. Okay, so far. Let's do one that doesn't work out quite like that. So I'm gonna give you a different function and a different point. Okay, so here we're gonna say g of x. And this is gonna be one more like what we did last year. I'm gonna give you a polynomial. Let's say we've got x squared plus 2x, and we want to find the equation of the tangent line at x equals, let's say 3. Get away from the ones and zeros and negative ones. Okay, well, here we do. We're doing that analytically. So how do we start the ball rolling here?
The limit last time?
Yep. We're gonna take that limit as h goes to 0 of, what's it gonna be this time?
X.
Okay, we're not using x's because we're going to find it at a point. That's what we did a lot of last year, was x plus h, f of x plus h minus f of x. But here we're gonna do f of 3 plus h minus f of 3 all over h. Okay, so we have limit as h goes to 0. What is f of 3 plus h going to look like?
3 plus h squared.
Nice. Keep going.
2, 3 plus h.
Plus 2, good, times 3 plus h. There's our f of 3 plus h minus the quantity. F of 3 is going to be 3 squared plus 2 times 3. With me there? Okay. Remember, I'm going to subtract that quantity. That's all over h. So we're going to get the limit as h goes to 0. Now we're going to square out 3 plus h. First one squared, twice the product, plus second one squared. First one squared is
9.
twice the product is
6h.
good. Second one squared is,
H squared.
all right. Continuing, disturbing the 2, we're going to get
6
good,
and 2h.
2h. Okay, should we just simplify everything in here? 3 squared plus 6 is going to be
16.
15, and we're just going to subtract that 15, and we still have it all over h. Ryan, are we okay? Okay, so it's going to be the limit as h goes to 0. So let's add these numbers, the 15, the 6, and the negative 15. What about all those?
I'll cancel out.
They're all going to cancel. So those don't have h's. And as we used to say all the time last year, anything without an h is going to cancel, and it does. So what we have left is going to be, let's see, a 6h and a 2h is going to make 8h, plus we've got that h squared. That's still all over h. Factor that h out, so we're going to take the limit as h goes to 0. We're factoring an h out of the numerator. That's going to leave behind
H plus 8.
good. And once we cancel the h's, now we are cleared to find that limit as h goes to 0. And when we do, that's going to be 8. So that we are calling g prime of 3, which is also the m, the slope for our tangent line. We need the tangent line. So we've done part A. Now, what else do we need to know besides the slope? A point. So our point is going to have x-coordinate 3, and I think we did that before. What did we say the y-coordinate was? Well, we can go 3 squared plus 6 again is going to be 15. So there is our point. Good to go? So point and slope. We have y minus the 15 is our slope 8 times x minus 3. And like I said, I'm a big believer in point slope because we will be doing this a lot. Find the tangent line. And the less arithmetic we do, the less likelihood of making an arithmetic mistake we will do. So you can stop right there. That is an equation of a line. Good to go? All right, I think we should do another. You can hear the clamor. This time we'll do a different kind of function. So we did a fraction, a rational function. We did a polynomial, and now we'll do a radical. So h of x is going to be the square root of x plus 4. And let's say we want to use here x is equal to 0. All right, where do we start? What is it?
The limit.
Yep, so we are going to take a limit as h goes to 0 of, waiting for it,
F of,
Oh, it's h prime 0.
it's going to be h prime of 0. So, yep, and so how are we going to do that? It's the limit of, I thought we were right there.
Square root of 0 plus
Oh, you're jumping. I'm going to write, yeah, you're right. So I'm going to say 0 plus h minus h of 0 all over h. That was, okay, that's before we plug it in, but you're exactly right. So that's going to be, Miranda's a couple steps ahead. So our h of 0 plus h is going to look like the square root of, what was it, Miranda?
2 plus 4.
H plus 4 minus the square root of
H plus 1. 4.
just 4 all over h. And we can say square root of 4 is 2. So we have limit as h goes to 0 of the square root of h plus 4 minus 2 all over h. What do we have to do to this?
you multiply by the conjugate.
Ah, exactly. We're going to rationalize that numerator because that's where the radical appears. So we're going to multiply top and bottom by the conjugate of the numerator. So square root of h plus 4 plus 2 top and bottom. So we will get the limit as h goes to 0. On top, we're going to get the difference of two squares. What does that look like?
H plus 4 minus 4.
Good. And on the bottom, we're going to leave it factored at h times square root of h plus 4 plus 2. Good so far. We can let those 4's kill each other off. Once they're out of the picture, we are now cleared to cancel the h's. And so we're looking at the limit as h goes to 0 of 1 over the square root of h plus 4 plus 2. Now that we have canceled the h's, we aren't going to get 0 over 0 anymore, which would have been indeterminate. But now we can plug in the 0, and we're going to get 1 4. That is h prime of 0, which is going to be our slope of our tangent line. Make sense? Kind of stuff we've been doing the last few days coming together a little bit in this, the limit stuff. And we also need a point, and the point is going to be
0,2.
very nice. And that happens to also be the y-intercept, so we can go right to our tangent line as y equals
1 plus x.
1 plus x plus 2.
very nice. There's our tangent line. Cool. What a good place. That's what I wanted to do for today. Do you want to do some practice problems for the test? I'll go ahead and shut this down. What kind of problem would you like to do?
Epsilon delta.
Another epsilon delta? You're not tired of epsilon delta?